Мгм.
Вот.
Ну что, да, давайте тогда начнем. Сегодня у нас выступает Anar Dosi из Харбина. So today our speaker is Anar Dosi from Harbin Engineering University. The title of the talk is Homological Framework of Noncommutative Complex Analytic Geometry and Functional Calculus. Please.
Yeah, okay, yeah, thank you. So let me extend um, my screen. Why is not operating here? Nothing. Is it visible like that or something?
Yeah, yeah, that's fine. Mhm.
Yes, fine.
Well, I think it's stuck up by a certain reason. I don't know why. So let me just. Oh no, it's not. It's not working. So let me do it again. Okay, let me try again. So. Ah,
Oh. Mhm.
why I have this space? I don't know. Yeah, anyway, is it visible like that, or
Yes, yes, that's fine.
I would have
Yes.
preferred the bigger scale? Anyway, yeah, okay, yeah, thanks for the invitation. Let me start. Sorry for the long title. So it's all about implementation of the Taylor's program. Well, I will try to do some attempt to completely implement it, just to be applicable to all possible cases. So the brief about topological homology. So the main underlying category will be Fréchet algebras, Fréchet spaces. So if I have an algebra of X is in a left module, all Fréchet. So we know what is meant projective resolution. So it's the family, the complex of left projective A modules with their connecting morphism, pi, so that this complex is admissible. Splits the complex of the Fréchet spaces. Well, if the algebra itself has the finite free A module resolution with the finite dimensional, these spaces, look, they are the free bimodules, but they must be a finite dimensional spaces, or sometimes nuclei will be enough. We say that A is of finite type. This is a general definition, what is meant algebra finite type. Okay. So what is meant derived functor? So we know what is that. If be another Fréchet algebra, if you have an additive functor, we can define nth derived functor. We need just to apply the functor to a resolution, to any projective resolution, and calculate homology groups. That's we use notation f and x. So if we come up with this sort of functor translating from the left by a right module, we use notation like that, torsion groups. Well, the two key notations of Taylor. The first one is transversality. So y in this relation with x. If by definition means all homology groups, they are vanishing for all n more than or equals 0. And another one, if y is an augmented right module. So look this argumentation here, the map for the fixed vector u in y. Then we define the dominance like that. This augmented model dominating over x. Yeah, by definition, again, the groups are vanishing for all n more than or equal 1. And as zero term, we have this topological isomorphism. So y from the left, x from the right. Result by using that u should be topological isomorphism with x. If this one happens, we say that we have a dominance. So two key properties of the Taylor's construction. Okay. Well, one more. We need localization. We know what is that. I had a several talk about it. So we have a continuous algebra homomorphism. B can be not necessarily Fréchet, any polynomial algebra into a Fréchet algebra. It's called localization if induced map of homologies for every bimodule, Fréchet A bimodule. So it's automatically B module, right? If this one implements the isomorphism of homology groups, we say that the map is a localization. Yeah, in particular, you can apply this tensoring of an inductive tensor product. So A over B will be A up to a topological isomorphism. Yeah, in particular, we have this one. Okay. So, well, the practical what we have to do to test this property. So we can take some admissible, the bimodal resolution of B, and then apply this functor tensoring from the left and right. And we can attach the multiplication map here. Yeah, if this complex is admissible for some resolution, actually for every P, then certainly is a localization in a bit strong sense. We say that it's an absolute localization or a stably flat over B. Yeah, in particular, we have this identification of the homology groups. And this one happens actually for every bimodule M. Well, there is another way. Sometimes the condition to verify this condition is a bit challenging stuff, but we can do the following. That's a result due to Taylor. So if we come up with the nuclear Fréchet spaces and say all the stuff here, they are nuclear, uh, if this complex is just exact, then the mapping is a localization. Yeah, that's a result due to Taylor from his original paper about general framework. Okay. Yeah, now let me start the categories, what I want to say. Some general constructions. This language is quite useful here. So we fix a unital Fréchet algebra and some category of Fréchet A algebras. So whatever stuff here, they have like that, look, that's object. This is another Fréchet algebra with the homomorphism, continuous homomorphism, which defines the structure of A algebras. Yeah, anyway, it's some category with the object and morphisms altogether. Well, briefly, we'll write like that. Look, A acting to S is a category. For example, we can just pick up all trivial modules of the source base algebra A, continuous characters, and this also category, right? So A to T. Certainly, if spectrum is not empty, I mean, we have the characters like that. Well, suppose we have an A category, A is an object here. Well, if you take the character, continuous character of A, certainly it's a character of the base A, right? So C mu is also trivial A module. That's why it's included to the category T. T is all the trivial modules. Well, if base algebra included itself into S, we say that S is a unital A category. For example, this category, just trivial modules, is not unital, right? A is not the T just consists of trivial modules. Okay. Well, again, what is my point complete? S may contain all trivial modules or not. Well, if it does contain all trivial modules, I mean trivial modules of all its objects, then we say that it's a point complete. Like all trivial modules, all points there. In this case, I can restrict just trivial modules. It's another A subcategory of A. Well, formally, we can complete S always by adding up just trivial modules and with their canonical morphisms. We can just always add them up here if we have them. And in this way, we can generate some completion. That's called point completion. Look, that's a notation for this one. Yeah, again, the routine, the terminology that I'm going to use, for example, when I'm saying that B is a local object, that means the map that we do have, right? Because B is a algebra is a localization. If it's a localization, we are saying it's a local object. If S consists of nuclear Fréchet algebra, we say that S is a nuclear category, like routine terminology. So what is the morphisms of 2A category? I mean, two categories like over Fréchet algebra. So that's also a routine, but there is something extra extra moment here. So suppose we have an A category, we have another B category. So we can define the functor. I mean, always a covariant functor. Well, but there must be also morphisms A to B of base algebras. This is a functor, but I wish also extra homomorphisms like A to F of A for all objects. And all it should be compatible morphisms. So if we have this one, then we say that we have a morphism of this sort of categories over Fréchet algebras. Look, this is our diagram, just the functor here, the base, all compatible. That's a morphism. Okay, now let's fix an A category. And look at the subcategory. Subcategory is said to be open if for every object and morphism in S, it contains the targeting object B as well. So once you have an object and a morphism from A to another one, that one will be also inside of this U. Okay, if this one happens, we say that U is open. Yeah, for example, trivial modules always will be inside of U, right? If A is an object of U, and certainly S is point complete. If you have trivial modules, they must be in. Okay, this is the open set. So this one generates topology. But this topology is a special topology. I mean, the intersection of all open neighborhoods of a fixed algebra is a set of all objects with the morphisms, right, from A to B. So this is again open set. So in this sense, S is an Alexandrov topological space. Like means for every A object, we have the least neighborhood, which is actually open quasi-compact set. Certainly it's not Hausdorff. It's a very special topology with the least neighborhood. Okay, yeah, that's the meaning of Alexandrov topological space. For example, if you have a trivial module inside of S, then from trivial module, there is nothing to another one. So just apart from identity, right? So that's why the least open is just itself, nothing else. So in this sense, the restriction is discrete over T. I mean. over trivial modules, which is discrete. Yeah, this topological, so every A category actually is a topological space. Yeah, what about closure of an algebra B, for example? Well, it's not so hard to understand that the B closure is actually consists of those objects with possible morphisms from A to B. So that will be exactly closure. Okay, for example, trivial module is closed here in the intersection because topology is discrete here actually. But in S, if you look at the closure in S, it's quite big, right? It may be B. It consists of those algebras such that lambda is a continuous character of A. That will be closure. Well, if S is unital, I mean base algebra inside of S, well, if you take this least neighborhood, that will cover up all space S, right? Because everything is here. We have morphisms from A to all objects. Yeah, in this case, S itself is a quasi-compact space, and this is a closed point. Closed point because nothing from the left, right? Nothing comes to A. Okay, that's a topological structure of S. It's not so hard, I mean, we can easily figure out what is that. Well, if we have a morphism, as I told you, what is that? There's a functor from S to another category, from A category to B category. Then we have this property concerning the least neighborhoods. This one actually means like functor, our morphism is continuous with respect to related Alexandrov topologies. That's good. So once having this one. Okay. Well, topology on S can easily be extended to completion, right? You need just to add up all trivial modules. For example, all trivial modules that corresponds to continuous characters of A, all inside of my least neighborhood of A. You're just adding up more points, I mean, more modules or algebras there. Well, but you can get completion and intersect with the trivial modules. Then you have the neighborhood filter base, right? All UA, the lambda is a character. This stuff actually generates a neighborhood filter base. Okay, I need several conception of the point base. Almost all of them are more or less the same, but since I have a general language of categories, I need to specify each time what is meant basis. Well, first of all, I don't need so much concerning countable, but anyway, let's say countable family of objects is said to be point basis if their least neighborhoods is a topology base in the point completion. If this one happens, we say that, look, we come up with a point base. Well, if this family consists of local algebras, I mean localizations, then we say T is a localizing basis. Okay, so if you take the trivial module from the completion, look, you can get this family, like lambda from here. This is a neighborhood filter base. So just a topology base, nothing else, just in the point completion. For me, it's important, like points, lambdas, they have the topology base like that. For example, you can get intersections, you can get closer to that point lambda. Okay, now let me introduce the spectrum. Well, suppose we have a category, an A category, X, the left Fréchet module. Well, all is Fréchet here. So let me pick up all algebras or objects like a resolvent from the resolvent set with respect to module X. So A is a point or whatever object from this set if this one holds, like for every morphism, again from this category from A to B, B is in the transversality relation with respect to X, because B is automatically a right module over base algebra. It's all happening over the base algebra A. Look, this is a definition of resolvent set. So we need to pick up all algebras such that for every morphism, B is in the targeting algebra is in the transversality relation with respect to X. Well, complement is called the spectrum. It's sort of a new spectrum of the module with respect to category S. Yeah, this is important to introduce, and you will see the link between the other spectra. But it's quite general and simple and nice. It looks very general. Well, what we can do here, we can restrict to tau, to trivial modules, like that. Well, that means in this relationship, we only use the trivial modules. Well, this one is called the Taylor spectrum of the module with respect to S. But if you choose just S, only trivial modules, this one is called the Taylor spectrum of the module. Look, that's a complement. So the Taylor spectrum consists of only trivial modules. And we also use notation like that, sigma AX. So it's a Taylor spectrum. Okay. Well, look at the definition here. So again, I can choose the identity morphism here, right? A to A that I do have in my category. So if you use the identity morphism, so you have this relation automatically. So resolvent is open. By the way, pay attention, there's an open set, right? Can you see it contains every B here? So spectrum is closed. Well, concerning the base algebra A cannot be inside of resolvent set, right? Because in the non-trivial case, if X is non-trivial, so this never happens. So that's why the base algebra should be included to spectrum. If our category is unital, it contains that algebra A. Well, if S is just T, trivial modules, that's a definition of resolvent set. All lambdas such that C lambda is in the transversality relation with respect to X. And this one happens when S is unit. Okay. Well, we need one more so-called Putinar spectrum. So look what I'm doing now. Along with this set, look, this is just trivial modules. Well, I can introduce something like that. Look, I can take this resolvent set. We know what is that. Take it completion. And look at all the trivial modules. Now we have a new set. So this set consists of only, characters, trivial modules. So C lambda belongs to here. That means there is an algebra from my resolvent set such that lambda is character, continuous character. Yeah, this is a bit a new set. but it consists of C lambda. So we can look at this completion again among the trivial characters, trivial modules. So this one is called the Putinar spectrum of the module with respect to S. Okay. Again, if you choose S to be just trivial modules, they're all the same. The Taylor and Putinar and our notation, they are the same. And one more moment here, Putinar spectrum and this Taylor spectrum with respect to S, they do relate to the points, right? To the trivial modules from the point completion. But our new spectrum, it consists of only algebras. So this consists of algebras from the S category, but these two guys, they are just trivial modules. So that's the difference here. Well, we know this property, let me say, if for every local, that means for every localization, this property for all characters implies this one. Well, we used to say the local transversality implies the global one. Then we say that X is an S local left module. Well, practically, it's all about Banach modules, the Banach case. There's a crucial difference. Well, that you can, maybe whoever now is familiar with the works of Taylor, you can see the similar result in the case of Banach modules, like locally parameterized. In this case, local transversality implies the global one. If this one happens, we say that the module is special, it's the S local left module. Yeah, why I need this stuff? If you wish, so far we have free spectra. If you wish to compare them, for example, what's the relationship between Taylor and Putinar? Yeah, here we need some technical conditions. For example, so first, A is of finite type. So it is a finite free bimodal resolution, a special one. S should be nuclear, a category, which has a localizing basis, looks so restrictive. In this case, Taylor spectrum with respect to S belongs to Putinar spectrum. We have this inclusion. Well, but if S is, if module is like Banach, let's say S local left module, then we have the density result. The Taylor spectrum will be dense in the Putinar spectrum, right? So under this condition, we can compare this Taylor and Putinar spectrum with quite a general case. That used to happen in reality in many examples. I show us this property, but this is quite a general result, technical result. It tells you, look, we can compare them. Okay. Yes, now I wish to formulate sort of spectral mapping theorem, again, in some sense. Okay, let's take an A category. And let's take some algebra, an object. Well, I told you this one defines the least neighborhood. Well, this is another A category. And I can talk about its completion as well, point completion. Well, but since it's a least open set, we now, they are all connected, right? There are all morphisms from this A to all objects here. So this one defines a new unital A category, this another A. So here, this A is a new base algebra, right? So, but we have also this morphism, right? Connecting morphism. This one can be extended up to a morphism of categories from this completion S to this one. Well, actually, morphism is quite simple. I mean, is identity over all objects from here and the trivial otherwise. So for every V, a category, we can restrict them. We can restrict, I mean, we can just look at this intersection here. For example, if you take this category restrict to A, that means just characters from this A. So just an elementary restriction to a new object A. Look how sounds the spectral mapping theorem here. So again, I need to have a finite type algebra, S, a nuclei category, which has a point basis. Let's take an object with its connecting morphism, but let's assume this dominance property over module X. Well, you can accept it like sort of the presence of a functional calculus. Sort of functional calculus happens with respect to new object A. Then certainly X is a new left A module, extending the original one. And look at the spectral mapping formula for all spectra. Look, first, this is our original spectrum. Again, this is a category restricting to A. You end up with this one. This is a Putinar spectrum trivial module. So again, you know what is my restriction to A, getting the characters from A. Result will be this one. And finally, for the Taylor spectrum, again, if you restrict, you end up with this one. Yeah, there's also a category here. Look, this is a spectral mapping theorem. That means actually, from this perspective, means like whatever happens, homologically happens over base algebra, we can lift up to a new object A under this condition. Yeah, this one can be treated like spectral mapping theorem. Certainly, there is no mapping here. I mean, no polynomials, nothing here. So, but we have this one again. Okay. Now I wish to attack the functional calculus problem. So that was the spectral mapping theorem. Next, I'm targeting something else. Well, I will put more restriction over category. Let's take now a category. Assume that is a pulsate category. So what is a pulsate category? That means the morphisms consist of at most one element, right? Only one morphism you can find here. For example, A to A, you have only identity. And the isomorphisms are only identity maps. Okay, that's called pulsate category. Well, if S contains the original algebra, then Hom A to B is a unique error, right? Because there should be nothing else here defining a algebra structure. Well, okay, look, this is a meaning of pulsate category. So we can define the order here like that. A less than equal B if Hom is not empty. This one defines a partial order structure on the objects. Well, in this case, the base algebra is a unique least element, right? Look, the base algebra is staying on the bottom of the picture here, of the structure. Look, this is my unique arrows here. And on the top, we have trivial modules, right? All the trivial modules, they are like sort of maximal elements. Yeah, roughly speaking, look, that this is that's a meaning of the pulsate category with the unique morphisms. Well, in this case, what's the meaning of least neighborhood? This is just objects from which are more than or equal A, right? It's a like right interval. So the topology here is just a right order topology of the poset. Well, what's happening with the morphisms? Morphism of the poset categories correspond to an increasing map, right? It's just order preserving map. A less than equal B, f of A less than equal f of B. Okay, for me, it's interesting the case when the poset category is actually a complete lattice. So we have a total soup and infinite. So just trivial lemma, the poset category is a complete lattice if and only if there exists infimum for every open set bounded below. So if you have an infimum for every open bounded below, that will be enough. Then it will be a complete lattice. So you can easily see that topological space will be a reducible topological space. I mean, every two open sets and non-empty open sets, they have a non-empty intersection out of the presence of a soup. So once having a soup, you can get intersections there. Okay. Now suppose S a unitil complete lattice A category. So A is the least element here, right? So S is a compact, reducible topological space. This is a characters, the inside of completion. Now look what I'm doing. The poset category, let me look at the open subsets of S. They I in turn generate a new category. It's also poset category. Let's say S tau. Right? The open sets here. We know the right order topology. Okay, let me look at this open sets, look at the opposite category. And for every open set, let me define infimum. Let me take the infimum. Right? Since we have a base algebra, so we have a lower bound. So infimum does exist. And look, we define actually a presheaf, the first algebra presheaf on S. Right? So again, S, a unique complete lattice A category. Well, I can look at the all open subsets. And look, this is a functor. We come up with the presheaf, fresh algebra presheaf. Well, so-called global sections, they actually the algebra A itself, because the infimum is A, right? The least one is A here. So this is my sort of global sections. Well, we can enjoy with this presheaf. For example, we can look at the stocks of S tau. If you look at the stocks, so stocks consist of all compatible families from the direct product. We can look at the direct product from the U and take the compatible families in the sense of morphisms from A to B. So global sections again, A. Well, if U is a just single point trivial, then the stock is just the trivial modulus, that's lambda. Okay. Well, if you take the morphisms of two unital complete lattice categories, we know what is that, right? F is a functor. We have connections A to f of A. Then it defines the functor of the open sets, right? So we can get the open set, look at the inverse. But our target to fix this, I mean, sort of category of open sets, because I wish to have a link to the category of presheafs. So that's why I need a strong morphisms here. So strong morphism, if it implements the category equivalence of the open sets. Well, roughly speaking, just open sets, open set categories, they are the same, omega. So the open sets on some topological space, we don't care about the topological space. Yeah, for example, identity map is a strong morphism, composed of strong morphisms, a strong morphism. So we end up with the category of all unital complete lattice categories with their strong morphisms. Well, the pay attention, this one has a common poset category of open sets. So the next forthcoming proposition tells you whatever I told here, just the copy of the category of all Fréchet algebra presheaves on omega. They are the same. Okay. Yeah, again, I took all the stuff here, unital, complete lattice categories with their strong morphisms. And that's exactly the same as Fréchet algebra presheaves. So for every presheaf, we can generate our category. P, look, that's a notation for this one. Okay. So now, let me introduce what is meant complex analytic geometry of A from this perspectives, because every time we have a problem with identifying the sort of general topological space associated with A and some sheaf or presheaf structure over it. But this definition is quite general, so we don't care about this particular topological space or whatever. Look, we are saying that by complex analytic geometry, we mean a unital complete lattice A category, such that for every open set, spectrum of the infimum, that's exactly in the completion, the point completion. So this one means like the spectrum of infimum should be just intersection of the point completion to trivial modules for every open set. Yeah, this condition is quite natural, and that's enough for me just to deal with the geometry. Okay, so it means the poset category of all open subsets in S induced by S consists of this one. Well, using our previous proposition, this one actually is equivalent, whatever I said here, the presence of a Fréchet algebra presheaf on some topological space, omega, little omega, which contains my spectrum of the base algebra, such that A will be like sort of global sections. And if you take spectrum intersect with U for every open set, this results in the spec of PU. Look, that's the meaning of this, this condition. So that means we need just family of algebras and their spec should define the topology, at least over characters. We don't care what kind of topological space we do have bigger than spec, whatever. Just we need this property here. Okay. Yeah, you know what has been this equality, right? Intersection means the natural sense. So every lambda is a character of A through the natural morphism. Okay. Well, if this topological space omega, that we don't know what is that, if it's reduced just spectrum of A, that means we come up with the Fréchet algebra presheaf on the set with this property. For every open set, we have this equality. Yeah, that's the meaning of the previous definition when omega is spec. In this case, we say that this couple is a standard analytic geometry of A. or you can treat like a category, corresponding A category. So you will see the more concrete examples of A with the standard geometric modules. Okay. Well, now we can talk about the spectrum. So once have a complex analytic geometry, we use notations like that, P everywhere appreciative, instead of categories. So we can define what is meant spectrum in this case. So you have a complex analytic geometry, X is the left module. We know omega is the topological space containing spec of A. So this resolvent set, open subset, look, it consists of points, gamma. But be careful here, that the point gamma means a point from omega that we don't know. What is that? Anyway, whatever here, there exists a neighborhood such that this property holds for every open subset. Look, this is just translation, whatever I told you about as categories in this particular case. Okay, this is a resolvent set. Complement is a spectrum. So if you take this spectrum, restrict to characters, we end up with the Putinar spectrum. Look, that's a link between them. So in general, omega is bigger than this one, but if you restrict here, we have the Putinar spectrum. But in the case of the standard analytic geometry model, like omega spec, so spectrum is actually reduced exactly as a Putinar spectrum, nothing else. Okay, so that's a moment. Like in general, pictures show that omega can be something larger than spec. But you have a spec here. If you restrict to characters, we end up with something familiar like Putinar spectrum. Okay. Yeah, again, point basis. What's happening with the point basis? I told you. Point basis turns out to be just a countable topology basis in omega that we don't know what is that. So the presence of a point basis routine, like, it's quite normal. Well, if there are localizations, we say that T is a localizing basis. And we also say that P is a localizing presheaf. Okay, that's a translation of the result, link between Taylor and Putinar spectrum. Again, A must be a fine type algebra with the complex analytic geometry. P is a localizing presheaf of nuclear algebras. Then Taylor spectrum will be inside of Putinar spectrum. And we have the density result if X is a sort of Banach module with a certain property. Look, the same result in terms of geometries. Analytic geometries, they look like that. Okay, now spectral mapping theorem can be translated here in terms of analytic geometry. So we need to select an open subset and define a new analytic geometry of the algebra. Look, by our definition, this couple is again geometry of P of U. And under the same conditions, the presence of the dominance, we have the spectral mapping theorem for both, like for Putinar spectrum and for Taylor spectrum here. Okay. Yes, now let me introduce finally what has been Czech category, just to formulate the functional calculus theorem. Yeah, here again we are turning back to language of categories because it's a bit different direction. We don't need too many restrictions here. So anyway, so as a complete lattice A category again. So we know what is that. Again, we need to select some countable family of objects. Yeah, it's said to be a basis if this one happens. So infimum can be taken by means of elements of the base from this category U. Well, in terms of the Fréchet algebra primitive, this is quite normal. I mean, topology base. Look, U is written like a union. If you take the infimum, that's a union corresponds to infimum, and we're getting this result. Okay. Anyway, so that's a link between this sense of a basis to a topology base, nothing else. Well, we know how to define the Čech complex, right? So let's do in this framework. So S, a complete lattice A category with the basis. I can pick up the tuples and look at their sup. Look, that's a supremum from the S category. Well, since it's a poset category, there are unique morphisms from BG to sup. Sup is bigger. Yeah, this notation is a routine. We know what is that. We need just to take the sups from the old tuples, look at their direct product. Okay, since it's complete, I mean, since they are countable, I end up with the Fréchet space here. And these are connecting morphisms. Again, construction is the same. At zero term, we have just product from the base B. A is an infimum of B. So we have connected morphisms from A to B. And this one defines, again, morphism to zero term. So look, we have a Čech complex. There's a bimodule complex of the base with the argumentation. Look at this connecting map. Anyway, this is just Čech complex, nothing else. So the category, you need to complete lattice A category is called the Čech category if this Čech complex is exact for some basis. Well, again, in terms of the preshafes, they are the same. Look, the sup is all about intersections. So we come up just the Čech complex of the covering. So it's analytic Čech geometry. We say that the omega p is an analytic Čech geometry of A. Okay. Well, if it's a sheaf, in the sheaf case, we know the famous result of Leray. If all finite intersections F are cyclic, so then Czech category means just omega should be F acyclic. Yeah, but not every Czech A category corresponds to a Fréchet algebra sheaf. For example, elementary tensoring sometimes end up with the presheaf, not a sheaf. But yet, this property holds. So you can get exactness here. Yeah, that's why it doesn't mean like a Czech category should correspond to sheaf. No, that's not true. And we have a more concrete examples below. Verification, this condition, first of all, let me say again, the verification exactness is not so hard. It's sometimes easy. Calculation of this Czech complex. Okay. Yeah, okay, look, this is my functional calculus theorem. Let S be a Czech category with a nuclear basis. X, finite free left module. If U contains the spectrum open neighborhood, then X is a left module over infimum, which lifts its A module structure. That is quite general functional calculus theorem. When this one happens, U should contain our spectrum. Recall that this spectrum is not a Putinar spectrum. Inside we have algebras here. Well, the corollary is known. Like, I mean, in the case of a standard analytic geometry, with the presence of a nuclear Fréchet algebra sheaf, then we know this result. So spec should be f-acyclic. Spec should has a countable base. All finite intersections must be f-acyclic. In this case, if X is a left module, finite free, and U contains the Putinar spectrum, we know this. Here should be Putinar spectrum, right? Open neighborhood. Then X, the A module structure can be lifted here. So we have a few functional calculus. Yeah, this is a corollary of this fact, promptly. Well, again, the same. You can formulate a spectral mapping theorem again. So we can skip it. So just a reformulation in terms of Czech geometry. What is that? But only the difference here, we have nuclear Fréchet algebra pre-sheaf here. So we are not assuming, so we have a sheaf here. Okay. Yeah, still I have a time. Let me say a few words about the example, because otherwise it's not interesting. Yeah, let's see the example, the concrete example concerning contractive quantum plane. So first example, let's look at this Arens-Michael envelope. We know this algebra is of finite type. The result, let's say, is the result. But if Q is less than 1, for example, as an omega, we can choose the spec. Actually, all reducible Banach modules, they are just one-dimensional, just trivial modules. Yeah, in this case, we know the precise structure of omega. It has left line, right line. So left complex line can be cubed with the Q topology. Yeah, again, I had a talk about it. So Q spiral and open sets. On the right, we can take just open disks centered at the origin. So left with the Q topology, right with the disk topology, all are non-Hausdorff topologies. So I can unify them, get a final topology such that both inclusions are continuous. Well, concerning the pre-sheaf structure, so I can get the standard sheaf of germs of holomorphic functions and draw it here to the left line. And in the same way to the right line. Look, I have a notation like OQ, OD. Look, this is a standard analytic geometry of the Arens-Michael envelope. This couple, look, this is a pre-sheaf projective tensor product. This indeed a pre-sheaf of Fréchet algebras, is not a sheaf. So with the Q multiplication, global sections will be A, and this is indeed a unital complete lattice A category. Well, concerning the bases, I told you point base or topology bases, we can choose Runge Q open subsets in the left-hand side, just open disk on the right-hand side and unify them. Look, we have a countable base here. So for this envelope, this couple is analytic Czech geometry. Again, we have the functional calculus theorem. So if open set contains the Putinar spectrum, then X is a left module. This result is true for any left Fréchet module. Yeah, localization problem here remains open. I didn't investigate it yet. Well, we know what is meant Fréchet module, right? It means a couple of continuous linear operators with this identity. By the way, in the Banach case, we have a very simple solution to the problem. Look, spectrum should be in UX, the S should be inside of UY. So here we don't need any joint spectrum. But in the general Fréchet case, probably we need the Putinar spectrum here. Okay. Yeah. So how to generate another geometries? Look, what can I do here? So we know what is an Arens-Michael envelope, right? We have to look at all actions to Banach algebras. But I can restrict this family of Banach algebras. It's a construction due to Oleg Aristov, so we can get another envelopes. For example, in our case, we can look at the actions to Banach algebras such that the Y is nilpotent. Y has a nilpotent action in B. If you get this class of algebras, we we end up with the new envelope. This is also Arens-Michael Fréchet algebra. Okay, let's say Y envelope. In the same way, we can generate X envelope, right? So if you calculate the characters, this one just represents the left line with the Q topology. So we can get this sheaf and tensoring this one with the constant sheaf. This is a sheaf indeed. So look, this one has a nice standard analytic geometry. Look, this one for CX for this Y envelope and this couple for X envelope. They are indeed very good in standard analytic geometries. Yes, we can talk about, again, functional calculus problem here in the general case. So if set contains the spectrum lies on the left line, right? So we have this functional calculus. Well, in the Banach case, I told you we have a couple with the nilpotent action of S. Putinar spectrum will be a closure of the Taylor spectrum. By the way, this closure can be quite large enough. Even in the finite dimensional case, it can be infinite set. So it's spiral until infinity. Well, this one actually tells you why Taylor spectrum is so poor in this construction. So we should take this one. Okay. Well, we can look at another envelope. For example, we can take the algebras B, which are nilpotent Banach algebras. Look at only this sort of actions. This one ends up with a new Rn envelope. You can choose just finite dimensional radical algebras. This creates another envelope. Well, in our case, these two envelopes are the same. It's just algebra formal power series. Actual result is true when Q less than or equal 1. Yeah, in this case, is a localization. Spect consists of a single point. Look, this is a geometry. Single point and stalk. This is indeed an analytic Czech geometry of this envelope. So this one representing just point here. Yes, again, functional calculus theorem works here. So let's take the null zeta Fréchet module. X is a left a module if and only if spectrum is non-empty. And in this case, certainly Taylor, Putinar, they are the same, just 0.00, nothing else. The origin. Well, when you have a left module, well, that's quite easy to understand when this one has a continuous action of X, if and only if both should be nilpotent operators. Again, Taylor spectrum here is also origin. Yeah, finally, a few minutes. So finally, the quite comprehensive picture we have in the case of the formal geometry. So in this case, again, CXY, both sides, we have the same Q topology. And we can define the sheaf, the fiber product from the left and right over the constant sheaf. Well, in this case, if you take the global section, this is a sheaf, and global section is reduced to the pi envelope. Again, this Alex's works concerning the pi envelope of the contractive quantum plane. Yeah, so in this case, this couple is a standard analytic geometry of the pi envelope. Yeah, again, we have the functional calculus here. That's a key result. So if you take Q open subset from this union of two lines containing the Putinar spectrum, then you have a few functional calculus. And we have a density result. Taylor spectrum is dense here. If X is a Banach module, in the case of a Banach module, we have density result. Yeah, here computation of the spectrum and the closure, they're quite non-trivial. So any exotic stuff may occur here. Yeah, concerning the when we have a global action, if and only if the multiplication should be nilpotent. So Banach module means multiplication should be nilpotent. Actually, this comes from the pi envelope. Okay. Yeah, this is a spectral mapping theorem, so we can skip it. So we have everything here. Yeah, finally, look, I can connect all. From all outer arrows, they all linked to the envelopes. So pi acting to left, to y envelope, also to x envelope, all results in the Rn envelope. The inside, we have the categories. So they're all morphisms of the categories here, or geometries, right? They all link to each other. So there are Oleg's envelopes here from outside, and inside there are geometries. Yeah, okay, yeah. Thanks for patience. Let me stop here. Okay, thanks for that.
Thank you very much.
Sorry
Thank
for the
you.
long talk.
Questions, please. So, does your general framework apply in, for example, in the case of formally radical functions that you constructed before over nilpotent Lie algebras?
Oh, yes, sure. The one
So this is
particular
another
case. So,
relevant example to.
yes, definitely, yeah, sure. Because that was idea, so to generalize all whatever I do have so far. So that problem solved for the nilpotent Lie algebra case and for this case. But this case was more exotic because I saw here something new that we haven't seen in the Lie algebra case. So this one forced me to extend this construction because that construction was a bit narrow, right, with the poor. So this one is quite general and applicable to both cases. Yeah, definitely. Yeah, sure.
And are there
But for
any?
me,
Yeah.
yes, please, questions first.
Yeah. Another question is, are there any news about the case where the absolute value of Q is 1, where the
Oh,
counterplane is
no,
not
yeah.
contractive?
Yeah, that's right. So again, so all my both examples, or all these examples of, we can say all of them also quite different examples. So we have a standard analytic geometry models. So that means we have a characters and presheaf. But so far, I don't know the example when we can construct some topological space bigger than characters and some presheaf there so that this framework would be applicable. I don't have this example yet. So when you said the Q equals 1, probably that's a case when we don't have a characters because characters are empty there. We have, well, we can choose the reducible representation. I don't know it. So we need to, but this construction tells you not necessarily take this one. We need just to build up some topological space, little omega that I told you, some Prishev, and that's it. Apply all this construction. If it works, down. So that's my feeling, because every time we had a problem, what might be this little omega, well, how we can find this, I mean, mysterious spectral. So, but this construction tells you you don't care about it. Find by any way, by some way. So, but you need just to have a Prishev over it and verify the conditions of this construction. If it works, so it's success. So you have a geometry. In this sense, again, this is a point of view of Taylor, right? Taylor's program to implement by somehow. Yeah, so I don't know this example yet. Would be great if someone else could find some new topological space and Prishev, which is bigger than characters, and implement this structure would be great. I don't have it. Yeah. Yeah, it's actually that's a good question. So,
Okay.
but
Okay,
I have
thank
no
you.
answer.
Thank you.
Okay.
Any other questions, please? Well, if there are no more questions, we thank the speaker again. Thank you very much for the interesting talk.
Good. Thank you.
Mhm. And well,
Yeah.
see you next Friday. So far, I don't know who our next speaker is, but so I planned someone, but the person whom I planned canceled his talk. So I have to find someone else. So
That's
I
not
will.
acceptable. So, shouldn't be canceled. Yeah, anyway.
Okay.
Mhm.